Hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video. Let's get straight into the action. We are going to be looking at similarity in right triangles. Are right triangles more special than other triangles for this? Sort of, yeah. There's something we're going to do specifically that works out this similarity as a result of the way that we divide things up. It's because of the right angle that really does a number that helps us. So we are going to look at similarity in right triangles. Work with me when it comes to the perception and how we dig it out. I'm going to be doing a lot of triangle redraws that will help us with this. And then we'll look at what are called geometric means. We are going to be doing right triangle examples involving geometric means as well as just looking at geometric means. If you don't know what they are yet, don't worry about that. We'll be getting into them pretty shortly here. All right, so similarity in right triangles. So first of all, let me present to you a right triangle. In this right triangle, I have legs A and B with hypotenuse C. The A and B make the right angle. The C is opposite that right angle. And I'm going to have these two other angle measures here. These are Greek letters. This is called alpha. It kind of looks like an A, if you will. And alpha will be opposite the A. And this beta, which kind of looks like a B, will be opposite your B here. So I'm going to be using those because eventually I'm going to kind of run out of variables. And they use Greek letters sometimes for angle measures, like if you've seen theta before. But I'm going to use alpha and beta here. Okay, guys. I'm going to rotate this triangle over. Hopefully you're okay with it. Ta-da! I rotated this triangle over because I'm going to draw what's called an altitude. An altitude is a segment that's drawn from a vertex to another side perpendicularly. So what's going to happen here in a second, you'll see in another slide, is I'm going to draw a little right angle that goes down there, right? It gives you the height between your side and that point. It shows how tall it is. So if an altitude is drawn from the right angle vertex of a right triangle to its hypotenuse, so if that's drawn like this, and I call that H right here, then three similar right triangles are made. Well, that is a bold statement that you make that many right triangles just by doing that. But it's true. It's true. It is. Now, the first question besides similarity is, where the heck are the three triangles here in all right triangles? Well, there are three of them, guys. There's a small one right here, and you'll see them brought about pretty soon. There's a small one right there. There's a medium-sized one right here, and this is kind of what I'm going to call them, guys. I'm going to call it the small, the medium, and then the big one, the original one. There's a big one right there. And yeah, they're all right triangles. Even that small one, guys, that small one right here, that's a right angle because these two are a linear pair, and they're both 90 degrees. So I'm going to actually get these drawn out separately and redrawn so they're all facing the same direction, and we'll prove similarity here in just a moment. So here's what's going to happen. First, let's firm up this H as if it really is part of a side thing. And let's separate the side length C as if these have these little parts X and Y. This will really help us distinguish what it is that we want to distinguish. I'm going to start with the big triangle here, guys. And when we take the big triangle, let's put it in green right here. In the big triangle, the smallest side right here is A, that short leg. I'll call it short leg, and then B I'll call long leg, if that's okay. So the short leg is A. I'll put it at the bottom. There's the right angle and the beta right there. And then there's the long leg B, which goes all the way to angle alpha. And then the hypotenuse, which before was C, I'm just now going to call X plus Y because it's the combination of those two there. I'm going to kind of keep consistent with as many variables, as few variables as I can. So there's that big triangle right there, organized and oriented in such a way that the right angle's on the bottom left, beta's on the bottom right, and alpha's at the top. Now let's look at the medium-sized triangle right here in purple. The medium-sized triangle features alpha, going to be at the top right here. Drawing down to the right angle is segment length Y, which apparently is the long leg. So long leg with long leg right there. And then we have short leg, which is H. Hypotenuse should be B. That's missing. I think on the next slide it should pop up there. Might have accidentally deleted something. I don't yet know what that angle is, but I think we'll be able to talk about that here in just a moment. And let's look at the shortest triangle here, which is in red. I don't know what kind of red that is. But as I said, this would be the right angle right here, guys. We know that beta is going to line up with this one here, bottom right. So in between the right angle and beta is the short leg X. H is the long leg here, and A is the hypotenuse. Now, I made a claim that these three triangles are similar, and they are. You know how they are? By using angle-angle. By using angle-angle, I can say that green is similar to purple. Notice how right angles are congruent and alphas are congruent. By angle, angle, green is similar to purple. Green's also similar to red right here because right angles are congruent and betas are congruent. Therefore, by angle, angle, those two are similar. And using kind of the idea of transitive property, guys, if green is similar to purple and if green is similar to red, then purple similar to red. It'll be the same kind of thing. And you know, there were those missing two angles here. I don't know if you know this, but by the third angle theorem, guys, these would have to be, if these two are congruent to each other, then these have to be congruent to each other as well. This has to be beta, and this one has to be alpha for the same reason that those two are congruent to each other, then these two have to be. So yeah, angle, 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 if you will, but of course we don't need all that. Now, why is it important to talk about triangle similarity? Because there are side lengths that are in proportion to one another. And in a right triangle, we'll have a short leg, a long leg, and a hypotenuse. Or at least two legs and a hypotenuse here. So, you know, you could write up certain proportions with these based on, especially with the redraw. I can't do this myself without doing redraws and having myself be helped a lot in the process. But listen, guys, we could do a lot of different proportions as long as parts correspond. I could say that A is to H, short leg and big is to short leg and medium, as long leg and big is to long leg and medium, as B is to Y. I could say something like the long leg in the medium is to long leg and small, Y is to H, as the hypotenuse in the medium is the hypotenuse in the small, as B is to A. And these aren't the only places that you'll see this directionality, but this is where they line up best. You can do it in this triangle thing as well. The problem is when you're trying to solve for a variable, you'll end up being kind of caught in the wind with, am I writing two variables in my equation for my proportion? And you don't want to accidentally make that mistake. This one will show you which numbers are variables and which ones are values and things like that. So there are a lot of proportions you can set up, and the redraws really do help. You probably won't see me not redraw them, with the exception of if you're only trying to find what's called the geometric mean, and you'll see when we run into that. All right, let's go ahead and do an example here, guys, where it says solve for all variables. Let's try and find y. Let's try and find z. Now, off the bat here, I don't know if you realize this, but we have actually enough information to find y and z without proportions whatsoever. These are right triangles, after all. If you notice this right triangle right here, you could solve for y using Pythagorean theorem, actually. Y squared plus 12 squared equals 15 squared. Now, I am going to solve using proportions. I'm just going to use Pythagorean theorem to confirm that this ends up being what it is that I expected it to be. I actually don't know what this is when I do this. 81. And then you get y, take the square root of both sides, you get y equals 9. So let's see if we can get y equals 9 eventually when we do this using proportionality. I'll leave that at the bottom. And, you know, z, we could have actually kind of done the same thing, really. We could have found out that, hey, here's a right triangle, and we could have said, in this case, z squared plus 12 squared equals 20 squared. And the thing is, guys, even, you know, like even for my students, actually, you know, there are times where, yeah, I might force it on them or to use the ratios and the proportions and stuff. But there are times where actually, you know, you are going to be forced yourself. Like, there's no way around it. You can't use Pythagorean theorem because you just won't have enough information. And that's going to happen as well. However, once you find certain information in your thing, then you can maybe resort to Pythagorean theorem if you want to, if it's easier, or, you know, if you like it more. So we're going to see if we can actually get that y is 9 and z is 16 the way that we did through Pythagorean theorem by using proportions. And the best way to use proportions with this, guys, for me to help you out best is by doing triangle redraws. I'm going to redraw this small triangle right here. I'll have it face the same direction as it did before. Y, 12, and 15. And let's check out the proportionality of the other ones. Let's redraw them exact same direction as this in terms of what corresponds here. So the medium triangle here in purple, what I want, y is, just by appearance, and now that you know that y is 9, but by appearance, guys, y is the short leg right here, right? Y is the short leg. So I want the shortest leg in the purple triangle to be down here. Is it z? Well, no, z was 16, and it looks longer than the 12 there. If you go by this thing, if you write the notes and you see which parts should correspond here, guys, if x is the short leg in the small triangle, h, the altitude, is the short leg in the medium triangle. So my altitude here, 12, is the short leg there. My long leg is z, and 20 is the hypotenuse. And in the big triangle, I'll just kind of draw in black here. In the big triangle, the short leg by number is 15, the long leg is 20, and the hypotenuse is y plus z. So now the parts correspond based on being oriented the same way. This will be a lot easier for me to write a proportion based on trying to pull out some numbers. I want to solve for y. So I want to write a proportion involving y and y only. I don't want to accidentally get z in it. I don't want to say something like y is to 12 as 12 is to z, which is correct. It just doesn't help me solve because that has two variables. So I'd rather use something that has just y in it, like y is to 12 as 15 is to 20. The short leg in the small is to the short leg in the medium, as the hypotenuse in the small is to the hypotenuse in the medium. That should work out right there. Okay. So, we can cross multiply and do stuff like that. I'll just go ahead. I'm going to reduce this stuff first a little bit. I'm going to reduce this fraction to 3/4. Yes, it's possible that I could reduce the 12 and the 4 together by multiplying both sides by 4. I'm going to keep it. Let's go ahead and cross multiply here so you can get some cross multiplication practice. 4 times y equals 12 times 3, which is 36. Divide both sides by 4, you get y equals 9. Hey, I've seen that before. Y equals 9, so that seems to have worked out. Now, guys, when you get y equals 9, you can replace your y with 9, and that can help you find stuff if you really wanted to, like 9, 9, 9. Maybe you couldn't find z unless you figured out what y was first, So that could be a setup there. And you know what? In fact, just to humor you guys, I'll go ahead and use, let me erase this now, but I'll go ahead and use one that did have y as 9 and find z with it. Let's have some fun. Let's use the one that has the 9 plus z right there. Okay. Let's say that the z right here, the long leg in the medium is to the long leg in the big, as the hypotenuse in the medium is to the hypotenuse in the big. So that's z over 20 equals 20 over 9 plus z. Oh, that's a quadratic. Did I do that to myself? I did. Hey, let's have fun with a quadratic for a moment. Do you mind? Let's do that. So 20 times 20 is 400. And here we have z times 9 plus z. Hey, never experiment if you don't want to run with something like this. Distribute here, we get 9z plus z squared equals 400. Oh man, this is not one that you would want to have some fun with. Maybe I shouldn't have done this one, right? Factoring. What two numbers multiply to make negative 400? I almost want to pause the video and do this part over. What two numbers multiply to make negative 400 and add to make 9? 25 and 16. So plus 25 minus 16, like that. This goes back. I don't know if my students know this factoring stuff. Hey guys, choose another set if you want to truly get that it's 16. But this is nice to look back at again. So z plus 25 equals 0 or z minus 16 equals 0. So z either equals negative 25 or z equals 16. Negative 25 is an impossible thing to have here because you can't have negative lengths. That's not going to work. Z equals 16 is proper. Anyway, that was one that I shouldn't have done. I shouldn't have delved into a quadratic. So don't get experimental. Try and use one variable at best if you can. But z equals 16 still works. I could have done so many other things under the sun. I could have done z over 20 equals 12 over 15. I would have gotten to the answer. That's fine. Anyway, hey, little quadratic work. Looks good. Let's move forward. All right, so that's similarity and right triangles. I'm going to do some more similarity and right triangle examples, but first I want to introduce you to geometric means, show you where it exists in right triangles, and use that after we practice some geometric mean stuff. So let's keep going. A geometric mean, what is one? It is the value that would exist between two values in a geometric sequence. If you don't know what a geometric sequence is, it's a list of numbers that are separated by a common ratio. If you don't know what a common ratio is, it's the number that you would multiply over and over to get to the next number in your geometric sequence. What's a geometric sequence? We just answered that. So here's an example, guys. Here's an example of a geometric sequence. 1, 2, 4, 8, 16, 32, 64, and so on. This is a list of numbers that you would multiply by 2 over and over to get from one value to the next, times 2 times 2. 2 is known as your common ratio. The values in your list are the 1, 2, 4, etc. So if I wanted to find the geometric mean of two numbers in this, of 2 and 8, well, that would be the number that occurs between 2 and 8 in a geometric sequence. In this case, that number is 4, because it's the number where you have to multiply by a common ratio. Remember, it's the same number over and over that you have to multiply by right here, here, and here in order to get from 2 to 8 with a number in between. 4 is the number in between right there. that is the geometric mean of those two numbers. So what I'm going to do, guys, is I'm going to explore the concept of the common ratio thing. By the way, 2, this number, comes from doing, if 2 times this number is 4, then 4 divided by 2 is that number. 2 is 4 over 2. 2 is 8 over 4. If I take a number in my geometric sequence and divide it by the number before it, I will get my common ratio. And I'm going to use this principle of these ratios and say, notice how they're equivalent. 4 over 2 is the same as 8 over 4 right there. So let's go to the next page. Let's take a look at trying to find the geometric means of some of these values here. Some values won't be integers. Most of them actually probably won't, especially when we get to the triangles. And let's see if we can make sense of doing something regarding proportions, though. Okay, regarding proportions. So let's say that I want to find the geometric mean of 6 and 24. That means in some geometric sequence, a 6 would appear, there's an unknown number, and then there's 24. That's how that works, right? I multiply 6 by some number to get this value, and then I multiply that number by the same common ratio to get that number. This is some unknown value, let's call it x. Okay, here's what's true. I don't know what my common, and listen, you might know what the answer is. That's great, but you won't for some of the other ones. So here's what's true, guys. I don't know what I'm multiplying by to get x, but I know I'm multiplying by the same thing to get 24. That means this is a consistent value right here. R can be also achieved and rewritten by doing, for example, 24 divided by x. If x times something is 24, then 24 divided by x is that something. R is the same as 24 over x, but it's also the same thing, guys, as x over 6. This divided by 6 is also r. That's what I was showing you on that previous slide there. And this is how we can write our proportions. That for a geometric mean, we can write our proportions in this format right here. That we divide the larger number by, I guess the larger number. Well, actually, I'm not sure if it's going to matter. But we divide 24 by x, and we divide x by 6, and we're getting the same common ratio out, right? So this is a proportion that we can set up to get this. And you're going to see me do this for all the other problems. So how do I solve for x from here? I would cross multiply right here, and I'd get x squared, hey, another quadratic, equals 144. And if I take the square root of both sides here, I get x equals plus or minus 12. Now that ends up being the answer for a geometric mean. You do get positive or negative 12. They don't ask you for the common ratio here, guys, but I could have multiplied this by 2 to get 12 and then 24, or I could have multiplied by negative 2 to get negative 12, and negative 12 times negative 2 is also negative 24. So plus or minus 12 ends up being your geometric mean. It's actually two different answers. And actually all of these will have two different answers because that square root thing. But when we start getting into lengths, guys, the negative answer doesn't apply because we can't have negative lengths. Right now, in this context, there are no lengths. This is contextless. What's the geometric mean of 4 and 25? We can do the same thing as we did before here, where you can say 25 over some unknown equals some unknown over 4. Honestly, though, you're probably going to see me write it the other way more, like 4 over that unknown is that unknown over 25. I just wanted to talk more about the common ratio to get it there. But I think this thing is a little easier for you to look at. Say 4 over this is this over 25. So just to humor you guys, I'm going to write it this way more. Just notice that the x is in the denominator of one and the numerator of the other. You'll be fine through cross multiplication. You're going to get the same answer. When I cross multiply, we're going to get x squared equals 100. And when you take the square root of both sides here, you'll get x equals plus or minus 10. Now, the number in between these two, so 10 is the number in between these two things here. You might not have known that you're multiplying by apparently 2.5. I know that number's 2.5. You're multiplying by 2.5 to get to the 10. You don't need to know that. We're just looking for the geometric mean. Oh, plus or minus 10, actually. You're looking for the geometric mean in between. All right, one more from 5 to 12. We'll do the same thing. 5 over some unknown equals that unknown over 12. So this is the proportion we're going to keep setting up for geometric means, okay? Cross multiply, you get x squared equals 60. 12 times 5 is 60. Take the square root of both sides. You get the square root of 60. It's not a perfect square. But you can simplify this radical. If you recall how this works, let's find the largest perfect square factor that can divide out. In this case, it's 4. And then, square, plus or minus, plus or minus. And the square root of 4 is 2. So you'll get plus or minus 2 root 15. See, not a very obvious answer that time. So plus or minus 2 root 15, that is the geometric mean of 5 and 12. So what do geometric means, now that you've seen a couple proportions, and hopefully you'll see this setup, me do this again. This is for, again, geometric means. What do geometric means have to do with right triangle similarity? Well, the length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. Whoa, that's a lot. So here's what we're saying. Remember the original right triangle right here? Here's the hypotenuse of that right triangle, okay? You see this altitude, h. H, this altitude, is the geometric mean of the lengths of the segments of the hypotenuse. Here's the hypotenuse. What are the lengths of the segments? X and Y. H is the geometric mean of X and Y. That means that in a geometric sequence, right here, you can do some sort of X over H equals H over Y. All right? Just like how we were doing before, the geometric mean is that unknown number that occurs in these parts. So X over H equals H over Y. Now, it's not necessarily the variables that you need, but it's the split part of the hypotenuse in the big triangle from the altitude. This over this equals this over this. That's what I'm going to be doing to find those missing lengths for any other problems that we do. And I've got 3 more problems to do, so let's take a look at those. And let's do the geometric mean parts first. Let's play with those first, and then maybe we can find some other missing lengths using Pythagorean theorem, if we're able to. So let's have some fun. Let's take a look. All right, solve for all variables. We have x, y, and z. I'm going to start with x. I'm going to start with x right here, guys. And I'm going to say, as x is the altitude of this thing here, I can say how this part's split. I can say 10 over x, this over this, equals x over 2. 10 over x equals x over 2. X over h equals h over y. X is the geometric mean of 10 and 2. So let's solve by cross multiplying. X squared equals 20. Take the square root of both sides. X equals, so this actually this time it's not plus or minus, right? Because this is length. So it's the square root of 20, which is root 4 times root 5, which means that is 2 root 5. So x equals 2 root 5 right there. We got 2 root 5. Okay. So cool. We use the geometric mean to figure out that part without needing to redraw all these triangles here. And without needing to redraw all the triangles, just for this one at least, I'm going to use Pythagorean theorem to find y and z in their own respective right triangles. In y, I could say that 10 squared plus 2 root 5 squared equals y squared. 10 squared is 100. What's 2 root 5 squared? Well, it's 20. Right? 2 squared is 4. Root 5 squared is 5. 4 times 5 is 20. So that's y squared. So that's 120 equals y squared. Take the square root. Y is the square root of 120. The largest perfect square factor there, 430. I guess it's still 4. So root 4 times root 30, that's going to be 2 root 30. So y is 2 root 30 right there. So let's take that, 2 root 30. And then to find z, you can either use Pythagorean theorem on these ones here, or you could go really bold and noble and use the big right triangle and say 2 root 30 squared plus z squared is 12 squared. I'm going to use the small one. Let's use the small one. I don't want to be too ambitious again. 2 squared plus 2 root 5 quantity squared equals z squared. 2 squared is 4. 2 root 5 squared, we said before, was 20. So z squared is 24. And z is the square root of 24. Once again, root 4 can pull out of there, and you'll get 2 root 6. So we got x is 2 root 5, y is 2 root 30, and z is 2 root 6. I never once actually had to redraw these triangles in any order because I was able to identify some parts using the geometric mean and then Pythagorean theorem. So if you think the triangle redraw gets too confusing and if you're able to go around it, give that a shot. Give a shot exactly what I just did right there. And, honestly, given that all these things are quadratics, I don't know how many times you'll have to do the quadratic thing I had to do with factoring. We'll see, all depending on the problem. All right, 2 more examples right here. I got another one. Let's solve for all variables. As you know, I'm going to go for x first because x is the geometric mean of 5 and 7. X is the geometric mean of 5 and 7, so we have this set up here. Let's go ahead and cross multiply, and we'll get x squared equals 35. Take the square root of both sides. You'll get x equals the square root of 35. Unfortunately, it doesn't simplify any more than that, so we'll get square root of 35. Now, I think you just saw Pythagorean theorem last time, so if you would like to try and do Pythagorean theorem on this one, why don't you maybe give this one a shot, do Pythagorean theorem on it if you'd like. I'm going to do the triangle redraw this time and see if we can get certain numbers based off that, see if you remember it. In this smaller triangle right here, I do have 5, root 35, and y. In the medium triangle drawn the same direction that corresponds, the shorter leg is root 35. I don't know if you guys know, but root 35 is indeed smaller than 7 because 7 is the square root of 49. And then here's a z. And in the big old triangle right here, the shortest leg, well, and the shortest leg is y. You're going to have to know about that. It's not just based on the drawing. You have to know something based on the concepts of what we kind of saw last time. But the shorter leg is y, the longer leg is z, and the hypotenuse is 5 plus 7, which is 12. You can see why you might not be as compelled to use this if you can use geometric means, because you have to set this all up just to kind of bring forth the rest of the problem here. Now, where is a set of values that I can use to, say, solve for y or z without conflicting the other? I don't know. Let's see. To solve for y here, y is to, here we go. We can use this one. Y is to 5 as 12 is to y. Short leg and big is to short leg and small, as hypotenuse into big is to hypotenuse and small. I had to use y more than once, though. Okay, I had to use y more than once. So that's y over 5 equals 12 over y. Cross multiply, you get y squared equals 60. I think you're going to have to do that several times. I think you're going to have to dive into the quadratic portion of this for these to work the same way that they do. Because y is, of course, a shared side in 2 triangles. Take the square root, we get that 2 root 15 that we saw on the previous problem. So y is 2 root 15 there. And I will put these in just in case, that might help us with z a little bit now that we have a little more information there. I don't want to make z too hard, so I'm not going to try and pull out too many radicals if I can help it. Let's go z is to 7 as 12 is to z. I'm going to try and just use only z's right there and no radicals. So z is to 7 as 12 is to z. And again, I'm drawing the arrows to show long leg and big, long leg and medium, hypotenuse and big, hypotenuse and medium. Cross multiply, you get z squared equals 84. Take the square root of both sides, you get z equals square root of 84. That's, if I divide by 4, I get 21. Yeah, I guess that's the smallest I can get. So root 4 root 21 becomes 2 root 21. And I'm guessing if you used Pythagorean theorem, you actually might have gotten to these answers a little bit faster than I did on that one. So I don't know. We'll see. All right, I got one more example. I know I'm running to the half hour. I know this one's longer. I just wanted to get a lot of geometric mean stuff in there. So one more set of geometric mean, guys. Here we go. Y is the geometric mean of 9 and 20. Hopefully you're kind of feeling out what I'm talking about there. So 9 over y equals y over 20. Cross multiply, you get y squared equals 180. Take the square root of both sides. Square root of 180 here. What's the largest? Let's see. 16? No, not 16. I don't want to spend too much time just trying to get the geometric mean part. 20 and 9. I guess 9. No, something bigger than 9. 36. 36. So 36 and 5. and that would give me 6 root 5 right there. So y is 6 root 5. Okay. I'll go ahead and I'll do Pythagorean theorem to get x, and then I'll use proportions to get z, if that's cool. So let's go ahead. Pythagorean theorem to get x. We got 9 squared plus 6 root 5 squared equals x squared, as x is the hypotenuse of this small right triangle here. 9 squared is 81. As we know, 6 root 5 squared is 180. And that equals x squared, which is 261. I wouldn't be surprised. Oh, no, that's not a... No, you can divide that by 9. Square root of 261. So that is 9. I don't know if that's the largest number, but 9 and 29. Yeah, it is. So that's going to give us 3 root 29 like that. So it's 3 root 29. Last one, let's go ahead and find ourselves that z. Let's set up some proportion here. Let's see if we can do it without a triangle redraw. Now that we know z is the only variable, let's see if we can do it without a triangle redraw. Let's say out loud some of this stuff here. Let's try and avoid using both sets of radicals, which means I might have to use z more than once. You notice how z is both the long leg of the big triangle, and it's the hypotenuse of the medium triangle. Let's try and use something with that, okay? The long leg of the big triangle is to the hypotenuse. Notice the reason I'm saying hypotenuse is because z is the hypotenuse of the medium. So the long leg of the big triangle is to the hypotenuse of the big triangle, z over 29, as the long leg in the medium triangle, 20, is to the hypotenuse of the big triangle, z. See, that might be hard for you to do without redrawing it, or Pythagorean theorem stuff. That's why it's a little confuzzling. Z squared equals, I think that's 580, and take the square root of both sides there. See, I'm doing this for the first time with you, so it takes a while to think about simplifying these things. I can definitely divide this by 4. I'll try and get something else after that from there. So if I divide by 4, guys, I get 146? No, 145. Is that right? Yeah, I get 145. I still don't know if 145 is a perfect square factor. And can it use 9? No. 145 divides by 5 and you get 29. No, yeah, that's it. So that's going to be 2 root 145. So bigger numbers. Obviously, simplifying radicals is a portion of what we're talking about now here, but those are my x, y, and z. Pythagorean theorem might be the way to go once you've established a geometric mean, but the proportionality is still in place, and it gets us to talk about what we said of the geometric mean with the x, h, and y kind of concept that we said before. And that's it, guys. I know that was kind of a lot, but that's it for this one. Thank you so much for watching Similarity in Right Triangles. Take care.